Hello everyone and welcome to the CP-31 Sheet solutions. Today we'll be discussing the 1600 rated problem to become max. This is Vibhaas Srivastava and let's get right into the problem. Okay, so let's navigate to the CP-31 sheet and we navigate to the problem. Let's open it up and read the statement. Okay, to become max, you're given an array of integers of length n. In one operation, you choose an index I such that I is between 1 and n minus 1. So you cannot choose the last element, anything except the last element. And a of I is less than or equal to a of I plus 1. Okay, so a of I is less than or equal to a of I plus 1. Then you can increase a of I by 1. Now what is our aim? We have to find the maximum possible value of max of a1 comma a2 comma an. So basically the maximum possible value of the max value of the array that you can get after performing this operation at most k times. Okay, so after performing this operation at most k times. Also, let's read the constraints. So the constraints are n goes up to 1000, k goes up to 10 power 8. So 1000, n goes up to 1000, and sum of n over all like test cases also does not exceed 1000. And also a of I goes up to 10 power 8. So this already gives us some clues, right? This gives us some clues. So before starting a problem, of course, we're gonna write down the expected time complexity, right? And here, as you can see, the expected time complexity is, I guess it would be something like big O of n squared, or because n goes up to 1000, right? So any solution of big O of n square, or maybe big O of n square log k, etc, etc, time complexities would pass. Okay, so that's what we expect, the expected time complexity for this problem. Also, what type of problem is it? So we can see that what is the problem asking us? It's asking us to find a maximum, right? So the problem is asking us to find a maximum, and what are the different techniques we employ to find like maximum, minimum, number of ways, etc. So you can guess that it's either going to be like greedy or DP or binary search, right? It could be some other topic as well, but most commonly when we have to find maximum, minimum, etc., it's going to be some either greedy, DP, binary search, or some combination of that. So before starting the problem, we have this much background knowledge, which through practice you would know that how to calculate expected time complexity, how to guess the expected topics for the question. All right, since a lot of students ask, how do I know what topic a question is, or how do I know what expected time complexity I have? So this is how we reason about it. Okay, now we're going to actually break down what the problem itself is asking. So what does the problem say? In one operation, we choose an index I, which is not the last index, and as long as it's less than or equal to the next value, we can increase it by 1, and we need to find the max value of a1 to an, right? So this is what the problem is asking us. So let's make an example array. All right, let's make an example array. Okay, and let's have let's just take some test case. Let's say 65415. All right, so we have 65415, which is an example which they've given us. Now we want to find the maximum possible value which we can reach here. Okay, so let's start by considering the last element. What happens to the last element? The last element always stays the same and it cannot be increased, because as you can see, the operation only affects indexes which are not including the last element, because the last element cannot be compared to the next element, right? So one simple observation we get right off the bat is last element cannot change, right? Last element doesn't increase, right? We're not sure if this observation will be useful or not, but it's good to keep in our mind that okay, we made an observation. All right, what about the second last element? What about 1? So what we know is, as long as 1 is less than or equal to 5, we can keep adding 1 to it, right? So 1 can become 2, right? As long as we have sufficient operations, 1 can become 2, it become 3, it can become 4, so on, and it can become up to 6, right? It can become up to 6, and it cannot increase any further. So basically, this can go up to 6 if we have enough operations. So let's just assume like we have infinite operations for now. We're just trying out, different cases. Okay, so this goes up to 6, right? What about 4? What can 4 go up to? So basically, since we have 4 over here, it can go up to 5, 6, 7, right? It can go up to 7 because right now we have infinite operations. So it can go up to less than equal to the previous one plus 1, right? And similarly for 5, right? 5 could go up to 8 and 6 can go up to 9 if we had enough operations with us, okay? Right. So what have we observed? Basically, we have observed like an increasing pattern, right? So if we had enough operations, we would basically get like last element, right? We would get last element. Then here it would be last element plus 1, right? Here we would get last element plus 2 and so on. So that's the pattern which we got from this example. Now let's take another example array. So example, and let's say we have 3, 1, 1, 1, 1, 10, 1, 1, 1. Okay, let's say this is our example array. Now let's use the ideas which we used before. So we saw that this element cannot change, the last element cannot change. This element can go up to 4. So if we had enough operations, we could make this up to 4. Similarly, this element could go up to 5. This element could go up to 6. This element could go up to 7, right? So according to this logic, this element could go up to 8. But as we see, this element is already the max. This element is already bigger than 8, right? So it can't go up anymore, right? This is 7 and this is 10. So this element will also never be able to increase. It will also be like stuck over here, right? It will not be able to increase because it's already larger than 8. Okay, it's already larger than 7, yeah. So then again we have a similar pattern starting here. So this can go up to 11 if we had enough operations. So here right now we're just imagining a k is infinity, so we have enough operations. This could go up to 12 and this could go up to 13, right? So here basically we're getting a pattern that like whatever, let this be the max element, right? Whatever, this is the max element, then the elements previous to it, prior to it, they all can be increasing arithmetic progression of 1, right? So from this we can make an observation which may be useful to us. Observation, let m equals max element, so max of a1, a2, an, right? Then our answer will be in the range m plus n. Okay, so basically the maximum possible value which we can reach for the any element in the array, even if we had infinite operations, would be m plus n. And the reason for this is simply because let's say the max element is here, then each element is being increased by 1 in turn, right? Increase by 1, increase by 1, increase by 1, and at most n elements can be increased. At most n elements can be increased. That's why the maximum answer goes up to m plus n. So I hope this observation is clear. The minimum answer can be m and the maximum answer will be m plus n if m is the current maximum of the array, right, in the start. Okay, so right now we're still in the phase of exploring the problem and getting some ideas, right? We know what we're looking for. We're looking for a solution which is roughly n square log something, n square log, etc., right? So right now we're thinking of like, is there a greedy idea, is there a DP idea, can we do binary search, right? And we have made some observations like the last element doesn't change, the answer will never exceed max plus n. So these observations we have made so far. Okay, so how do we follow up on this? So yeah, so now we're gonna have an idea. Okay, what if I know my answer is in the range m to m plus n, right? I know my answer is in the range m to m plus n. So obviously when we think about problems, we would like to try each idea one by one and we would try to see if it works. If you try to think of greedy ideas, it would be pretty clear that greedy ideas won't work because we don't know how much to increase. For example, if you think of just greedily increasing as much as possible, what if you overshot? What if you increase too much and then later you didn't need to increase that much, right? So that's why greedy ideas won't always work to solve this problem. So we try to look at either DP or binary search solutions, right? So let us try to think about binary search. So obviously to test out this, you can try out the examples. You can figure out why greedy does not work. That comes with intuition. So we'll try to think of some binary search approach. For binary search, what are the things we need, right? What are the things we need to do a binary search? We need first the range of the answer. So we already have the range of the answer. This is the range, right? We thought about it already. Then the other thing we need is range. So basically L and R, right? The second thing we need is for the answer to be monotonic, and obviously it's monotonic here because monotonic because if we can reach a max less than equal to some value, then those will be true, right? If we can have a max, if some value less than equal to this is reachable, then we can have true for that, and anything larger than the max can return false. So that's why we can say that this sequence is monotonic, and we can do a binary search over the sequence to find the maximum value which returns true, right? Now we actually have to implement the function itself. So we need a check function, right? Predicate function or check function. I'm just going to call it check function. And what does the function do? Formally, you would call this a predicate function which returns true or false, right? So what does this function check? It just checks if um is it possible to attain a max value, to attain a max a of I that is greater than or equal to x, right? So given an x, check of x and the array A basically returns, is it possible to attain a max of A of I that is greater than or equal to x with k operations, right? Because that's the key idea, that we have at most k operations. Okay, so basically now our goal is to see if it is possible to implement this check function at most in n square, right? At most in n square, because we know the solution n goes up to 1000, so we can have like n square log n solutions, right? So we need to somehow try to do this in n square. As we are thinking through the problem, we might be considering many approaches, greedy, DP, binary search. So we think through this and we think, okay, can I do this in n square? Can I do this in big O of n square or less? Then I will have a binary solution, right? Then I will have a binary search solution. I will have a simple binary search solution. A simple binary search solution, right? Okay. So how do I go about this, right? So again, we need to break down the problem, and we know that so assume the target max, right? Target max is achieved at a position I, okay? At a position I, right? So let's say our array was something like 3 2 1 1 6 5 4 2 3, okay? And we have some value of k. So I'm not going to define the value of k, and let's just choose some position I. Let this be position I. Let this be position I, and let's assume that our target max, which is like some x, right? And we need to make sure that the max is greater than or equal to x. That means we can achieve at least x. So that means we can achieve at least x with k operations. Let's assume that this is our target max and this becomes x, right? So this position I of the array becomes our target max x, and this is the position where the target max is achieved. Then we know that the next value should be at least x minus 1, right? The next value should be at least x minus 1. Similarly, this next value should be at least x minus 2, and so on, right? This must be at least x minus 3. And now here, since the next value is larger, right? Since the next value is larger, we know that it might be possible. So basically, let the target max be 8. Okay, let our target max be 8. Then this position would have to go up by 2 to become 8, right? That means this position was at least 7. So what are we doing here? We're basically reversing the pattern we saw earlier. Earlier we saw that, right? This will be 3, then this will be 3 plus 1 4. It can reach, this can reach 4 plus 1 5. Here we're saying that this has already reached 8. Then that means that the previous one must have been at least 7, right? Similarly, the previous one to that must have been at least 6. And the previous one to that must have been at least 5, right? And that means the previous one must have been at least 4. And now we can see that obviously 8 is not possible here. We can return no, because we can see that 3 is less than 4, and we cannot increase 3 to 4, right? If we take 2 operations, we can increase 6 to 8. Similarly, we can increase 5 to 7 with 2 operations, but we can't increase 3 to 4. Okay, so this is a way to check. So basically, given a position I, a target x, as well as k operations, how to check, right? How to check if it's possible. So we can write a loop. And what will the loop look like? It will be something like this. So we want a of I to do some operations and reach the target x. Similarly, if a of I plus 1, we want it to reach x minus 1 at least. Similarly, a of I plus 2, we want this to reach x minus 2, and so on, until like if x was like, if a of I is already greater than or equal to x, then the answer is simply yes, right? Otherwise we need to count the operations it takes to go here, right? So basically that's what is going on. And similarly, if here a of I plus 1 is greater than or equal to x, then again the answer is simply yes. Otherwise we need to count the number of operations. The number of operations here will be x minus a of I, right? Because that's the number of increases we have done. Here also the number of operations will be x minus 1 minus a of I plus 1, right? And so on. Now let's say at some point it becomes a yes. At some point we get a yes, right? Then the total number of operations which we get by summing these, right? These should be less than or equal to k, and then we can return yes, right? So for some position I, we can test if that position I could reach the target x. That would mean that the next position can reach x minus 1, the next to next can reach x minus 2, and so on. And in that case, we can count the number of operations and if that's less than or equal to k or not. Okay, so this is going to be the high level idea. Let me give you an example. And we can see that for some position I, this strategy works in big O of n using a greedy method, right? Using a greedy method, this strategy works in big O of n. So trying it for all I will be big O of n squared, right? So trying it for all positions I, we can assume that all positions I one by one can be the target. So we can do that in big O of n squared. But yeah, let's not get ahead of ourselves. Let's see an example for how to do this. Let's take an example, okay, to explain what I meant by this. So basically, let's say we have again 1, 2, 3 and 6, maybe 5, 4, 7, 1. Okay, we have something like this, and we have, let's say, number of operations will be let's say 10 operations. Okay, and we want to find some max. So let's say we are given some position I. Let's say we're given this position I, right? Or let's say we're given this position I, and we're also given our target maximum as, let's say, 9. Okay, we're given a target maximum as 9, and we have to check if we can make this position into 9. All right, so to make this position into 9, that means this position must be 8, right? At least 8, and then this position must be at least 7. But here further we don't need to check because this was already equal to 7 or larger, so we can stop checking here, right? That's how the pattern worked. Basically at every maximum we can start like 7, 8, 9, like that we can increase. So that's why we only need to check to this point and we need to see how many operations it takes. Okay, so to make 5 to 9, how many operations is that? 5 to 9 is 4 operations, right? 5 to 9 is 4 operations. Similarly, 4 to 8, that's again 4 operations, right? And 7 to 7 is 0 operations. So as we can see, total 8 operations were taken. 4 plus 4 equals 8 operations. Is 4 plus 4 equals 8. Total number of operations we have is 10. So this is less than 10. So we know that x equals 9 is achievable if we start at this I position, right? So that's how we can test for each I position. We can try to make this equal to 9. Then we can try to make this equal to 9 and so on. If it works for any of the position, we can return yes. All right. So that's basically the idea. How do we get the intuition for this? The intuition is basically for each position. This is the intuition for each position. We try to make it equal to, for each position I, we can try to make it equal to our target max, x, using the above observations, right? Using the above observations. What were the observations? Basically the values form like an arithmetic progression, right? Like if we have the current value is x, the next value will be x minus 1, x minus 2, so on. That's how much we need to increase until we hit some value which is already greater than equal to whatever x minus n we have, right? At that point we can stop. Also, we need to keep in mind that last value cannot be changed. So last value cannot be changed. So if we want to increase the last value, we can simply say that that case is not possible, or we can put a cost of like infinity on it, right? Also, last value cannot change. So let's say we have like our target was 10. Let's say our target is 10 and we have something like 555, right? So we want this to be 10, so we want this to be 9 at least, we want this to be 8 at least, but this last value cannot change. So that's why this will not be possible, and we can put a cost of infinity on this to say that okay, it's not possible, right? Okay, so let's put this all together. Let's put it all together. Okay. Okay, solution. Putting it all together. Okay, so the first idea is our range of answer lies between max of the array, so max of the array, max of a of I, that's what m is, and max plus n, right? And we showed this in the very start. So we can set L equals m, R equals m plus n. We can do binary search. Basically while L is less than R, or whatever form of binary search you prefer, right? I prefer the L less than equal to R form of binary search, but that is up to your preference, right? Yeah, and then we can do a check. So if we define mid as obviously L plus R by 2, right? That's how binary search works. If check of mid, if it's possible to have this maximum, then update the maximum and do the corresponding binary search, so on. Go L equals mid plus 1, and here R equals mid, right? Else R equals mid, or however you want to implement the binary search. Just be careful that it does exactly what it does. So obviously with some binary search practice you would be perfectly fine with this, right? Okay, and how do we check if a particular mid value is possible? We can try for each I position, right? For I equals 0 to n minus 1, we can try to make it equal to mid. And for this, basically we need to start at, let's say, j equals I, and let's say y equals x, right? So we need to make it equal to some target x, and while j is less than n, we can do j plus plus, y minus minus, because we need the first one to equal x, the second one equal to x minus 1, then x minus 2. So that's what this y is. This y is simply that x minus 1, x minus 2. Okay, and we can simply say that if y is less than or equal to a of I, then we can break and we can say that, yeah, if the number of operations was less, then we can say it's possible, right? So we need to count the number of operations taken. Operations will be 0, right? Otherwise number of operations will increase by number of operations will increase by how much? The amount of difference between a of I and y, right? It will increase by y minus a of I, right? Also, if j is equal to n, that means it's the last element, so it's not possible, right? So if j equals n minus 1, operation becomes infinity, right? All right, so now if we can say, if the number of operations is less than or equal to k, that means it's possible, we can return true. Now if for all I it's not possible, then we can return false. So outside here we can write return false. So this will be the pseudocode for our check function, right? To check a particular value based on the observations we have done. It's a brute force plus greedy. So basically for each I we are trying, so that's almost brute force. And then for each particular I, we're doing like a greedy approach using that pattern, right? Using the pattern that it's going to be x minus 1, x minus 2, until it hits a value where it can just directly take it. So that's what we're doing here. X and y is going minus minus, so x minus 1. We're comparing if how many operations are taken. If the operation is less than or equal to k, we can return true. Okay, so that's how this one works, right? So let's now analyze the time complexity and memory complexity. So as you can see here, this loop takes big O of n, and this loop also takes big O of n. So we can write the time complexity as n squared for the check function, right? So time complexity is n squared for the check function, and as we know, binary search time complexity is the time for the predicate function multiplied by log of the range, right? Log of r minus l. So how much is r minus l? That's simply n. So the time complexity will be big O of n square log n, right? Which is more than enough for the constraints. N goes up to 1000, which is quite less, right? We could have had a slightly higher time complexity and still passed. What about memory complexity? No additional memory is being created, right? No additional memory is being created. We're just doing checks on the given memory. So you could say the memory complexity is simply big O of n, or additional is big O of 1, right? Additional memory uses big O of 1 if the array is already like defined in memory. Okay, let's have a quick look at the code. So let me just write the time and memory complexity here itself so we can have a reference, right? Time complexity is big O of n log n, and memory complexity is big O of n. Okay, right? So let me get to the binary search logic first. So we have the test cases. We take nk. We're defining nk and the vector a globally because that helps us during our check function, right? We take the input. L is defined to be the max element of a. As we said, L equals m and r equals m plus n, right? So r equals L plus n. And the way I'm doing binary search is having L less than equal to r. This is what I prefer. If you want, you can do whichever variant you want, L less than r. I prefer this variant because it's more foolproof. It's harder to make errors with this, right? And my answer will be equal to L. Here my L goes to mid plus 1 and mid minus 1. So it makes sure that each step of the binary search, L and R change. Okay, so that's why I keep it like this, L less than equal to R. So mid is defined as L plus R by 2. Since L and R are fairly small, there won't be any overflow issues. We check the value of mid. If it is true, we update the answer. L goes to mid plus 1, otherwise R goes to mid plus 1. Once we're done, we print the answer. Okay, so now the check function itself, for each I from 0 to n minus 1, we try that I as our maximum. We have a cost variable set to 0, and we run a loop, basically the same loop. J starts at the ith element and goes until the end, basically. y is x minus 1, and so on. If it is less than a of j, we can just break. Otherwise, if it's equal to n minus 1, then the cost will be infinity, so we increase the cost by infinity. Otherwise, the cost is increased by y minus aj, which is number of operations taken. So cost is basically number of operations here. Okay, so number of operations, right? And if this cost is less than equal to k, we can return true. If for no y this worked, we can return false. All right, and we can simply run this code. It runs pretty smoothly on the test cases. You can just go and submit this again. Why not? And so yeah, it's taking a while to judge, but as you can see, I just submitted this just a while back, and it runs pretty quickly, 62 milliseconds with 0 KB of memory. And yeah, for the constraints, that's pretty good, right? All right then. Some tips if you had trouble with this solution is, if you had any trouble with the solution, then first thing you could have the trouble with is not knowing if it's binary search, right? So in that case, you just need to understand the pattern of binary search, right? Pattern of binary search, to always have in the back of your mind that the question could be binary search, and how to think in that terms, right? So this will come if you learn binary search. Maybe you're not that clear with the fundamentals, or you want to practice more problems on it, right? Practice problems. Even if you knew it earlier, you might get rusty, so it's always good to practice from time to time. As you can see, it's accepted roughly the same time. Obviously small variations will be there, right? And if you understood it was binary search, but you're not able to think of this logic, then you would need to practice more greedy problems, I guess, right? Because the way we work on the predicate function is using greedy. All right, so that's all for this question. Thank you for watching. Hope you learned something. If you are any stuck at any point, definitely do pause the video, rewind, and try them out again. Okay, thank you, and see you next time.